Before the rise of the Islamic Golden Age, the world of the 7th and 8th centuries stood at an intellectual crossroads. The once mighty Sasanian Empire, whose scholars preserved centuries of Persian, Greek, and Indian knowledge, had fractured under the strain of internal conflict and prolonged war with Byzantium. Byzantine cities, described in the chronicles of Theophanes the Confessor, struggled to preserve fragments of ancient Greek learning while political turmoil drained their resources. Much of Aristotle, Galen, Euclid, Ptolemy, and Archimedes survived in scattered monasteries. In Syriac translations guarded by scholars like Sergius of Reshaped, or in decaying libraries of Alexandria long after its decline. When early Islamic armies encountered these lands from Syria to Persia, they found not ignorance but fragmented knowledge, libraries half abandoned, manuscript houses struggling, scholars dispersed. This is noted by the 10th century bibliographer Ibn al-Nadim in his Fihrist, a monumental catalogue of books circulating in the Islamic world. He lists Greek, Persian, Indian, and Syriac works, some nearly lost, indicating that early Muslims inherited a mosaic of intellectual traditions in need of preservation and unification. In the decades after the rise of Islam, vast regions from Egypt to Persia fell under a single political sphere. Unlike earlier empires, however, the new rulers showed a remarkable openness to integrating the knowledge they encountered. Chroniclers like Al-Tabari record that during the Umayyad and early Abbasid periods, translators and scholars increasingly moved to emerging centers such as Damascus, Kufa, Basra, and later Baghdad. Persian scholars trained in institutions like Gunda Shapur, whose academic legacy is referenced by medieval writers like Al-Kifti, became early contributors to this growing intellectual world. Syriac-speaking Christian scholars, inheritors of the Alexandrian and Antiochene schools, brought with them centuries of translation work. What made the Islamic world fertile ground for a scientific renaissance was not merely conquest, but the unification of languages and institutions. Arabic became the lingua franca of administration, literature, science, and philosophy. Unlike Greek, which remained confined to limited elites, Arabic spread rapidly across regions, becoming a powerful scientific language capable of expressing mathematical precision, philosophical complexity, and medical detail. The historian Dimitri Gutas, in his study Greek Thought, Arabic Culture, explains that the translation movement thrived because Arabic had been refined through Quranic scholarship, grammar, and poetry, making it flexible enough to absorb foreign concepts while giving them new linguistic structure. Early Islamic rulers began encouraging scholarship in deliberate ways. Caliph Umar ibn Abdul Aziz, known for his reforms, is described in later chronicles as supporting learning and literacy. Under the Umayyads in Spain and the Abbasids in the East, paper, introduced after the Battle of Talas in 751 and later produced in Samarkand and Baghdad, transformed book culture. This technological shift is detailed in the writings of Al-Jahiz, who notes that paper was cheaper and more durable than parchment, allowing libraries to grow in size and accessibility. As trade routes stabilized under unified governance, books, scholars, and ideas flowed freely across continents. Mathematical texts from India, such as Brahmagupta's Brahmasfuta Siddhanta, reached the court of Caliph al-Mansur, as described by later historians of astronomy like Al-Biruni. Greek philosophical works from the eastern Mediterranean arrived in Damascus and Baghdad through Syriac intermediaries. Persian administrative sciences blended with Arabic linguistics and Islamic jurisprudence, creating new methods of categorizing knowledge. This intellectual unification was not accidental. It reflected the values expressed by early Muslim thinkers who emphasized learning as a form of worship. Scholars like Ibn Ishaq al-Kindi, later known as the philosopher of the Arabs, argued that wisdom was universal and belonged to whoever sought it, a sentiment echoed centuries later by the Andalusian polymath Ibn Rushd. These attitudes created an atmosphere in which scholars of every background, Arab, Persian, Berber, Jewish, Syriac, Greek, and Indian, could contribute to a shared civilization. By the early 8th century, conditions were set for something the world had not seen since the height of Alexandria, a civilization prepared to collect, translate, expand, and transform global knowledge. This was not merely a revival, it was the foundation of a scientific revolution that would span centuries crossing borders of faith, ethnicity, and empire. At the heart of this emerging intellectual world, a single city began to rise as the gravitational center of global knowledge. Baghdad, founded in 762 CE by the Abbasid Caliph al-Mansur, was not built as a traditional capital. It was designed as a city of learning, a circle within circles, intended to symbolize unity, order, and cosmic harmony. Medieval chroniclers such as Al-Yaqubi and Almas Udi describe its construction as one of the most ambitious urban projects of its age: wide avenues, specialized quarters for artisans and scholars, and palaces surrounded by libraries that would soon house texts from every civilization that touched the Abbasid world. Baghdad's rise as an intellectual powerhouse accelerated under Harun al-Rashid. The caliph celebrated in the 1001 Nights, but far more remarkable in historical reality. His court employed scholars, poets, translators, and mathematicians, whose names survive in biographical dictionaries like Ibn al-Nadim as Fihrist and Ibn Abi Usaybi or as History of Physicians. These sources describe a vibrant scholarly community where Greek philosophers, Persian astronomers, Indian mathematicians, and Arab linguists worked side by side. But it was Harun's son, Al-Mamun, whose reign transformed Baghdad into the world's greatest intellectual hub. His passion for astronomy and philosophy is well documented in early sources, such as Al-Tabari's Chronicle and later by the historian Al-Mas'udi, who recounts that Al-Mamun experienced a dream in which Aristotle appeared to him, urging him to seek truth through reason. Inspired by this symbolic vision, recorded in both Arabic and medieval Syriac sources, Al-Mamun launched an unprecedented scholarly campaign, collecting manuscripts from across the Byzantine Empire, Persia, India, and Central Asia. To house this extraordinary influx of knowledge, Al-Mamun formalized what earlier caliphs had begun: the creation of the Bayt al-Hikmah, the House of Wisdom. This was not merely a library. It was a research institute, translation academy, astronomical observatory, debate hall, and scientific laboratory combined into one. The historian George Saliba, in his extensive work on Islamic astronomy, emphasizes that the House of Wisdom institutionalized scientific innovation, making it the first true research center in history. Under Al-Ma'mun's patronage, the House of Wisdom attracted scholars like Hunayn ibn Ishaq, the Syriac Christian polymath who mastered Arabic, Greek, and Persian and became the most influential translator of antiquity. His methodical approach, examining multiple Greek manuscripts of the same text, comparing them line by line and producing a corrected Arabic edition, was revolutionary. Hunayn himself described this process in letters catalogued by Ibn al-Nadim. His translations of Galen, Hippocrates, Plato, and Aristotle created a shared intellectual foundation previously unavailable to any civilization since the fall of the Roman Empire. Alongside Hunayn worked mathematicians such as Thabit ibn Qurra, whose translations and original works in geometry and number theory expanded on Euclid and Archimedes. Persian scholars trained in the medical schools of Gundashapur, such as the Bakhtishu family, brought with them centuries of Sasanian scientific knowledge. Indian astronomers contributed treatises on planetary calculation and trigonometry. From every corner of the known world, the House of Wisdom gathered specialists whose skills converged into a single scholarly engine. Baghdad's scientific landscape extended beyond its academies. Al-Mamun established observatories, described by the geographer Al-Khwarizmi and later by the historian Al-Kifti, where astronomers measured planetary motion, refined astrolabes, and produced star catalogs surpassing Ptolemy's Almagest. Al-Mamun himself sponsored an expedition to measure the Earth's circumference, an event recorded by Al-Biruni centuries later. Teams of surveyors walked the plains between Tadmor and Raqqa, calculating Earth's size using triangulation and celestial elevation, arriving at results astonishingly close to modern measurements. Baghdad's intellectual atmosphere affected every discipline. Jurists debated law using logical methods that came from Aristotle. Physicians read Galen in Arabic translations and produced medical encyclopedias that would dominate hospitals from North Africa to Central Asia. Poets blended Bedouin oral tradition with Persian literary aesthetics. Mathematicians, exploring algebraic symbolism inspired by Indian numerals, laid the groundwork for the era's greatest mathematical breakthroughs. What made Baghdad extraordinary was not only its scholars but its openness. As the medieval Andalusian historian Ibn Hazm observed, the Islamic world's scholars came from every religion and ethnicity, Muslims, Christians, Jews, Zoroastrians, and others, working under a shared intellectual language, Arabic. The Golden Age was not the triumph of a Singh. The translation movement that flourished in Baghdad did far more than preserve ancient knowledge. It transformed it. What began as an effort to gather the intellectual heritage of previous civilizations soon evolved into one of the most ambitious scientific enterprises in human history. Under the Abbasids, the Islamic world became the great bridge of knowledge, linking the past to the future through meticulous scholarship, commentary, and innovation. The scale of this translation project is known to us through bibliographical works like Ibn al-Nadim, Sfihrist, which lists thousands of manuscripts circulating in Baghdad by the 10th century, works of philosophy, astronomy, medicine, mathematics, alchemy, geography, and logic. These catalogs show that Arabic became the universal scientific language of the age, replacing Greek and Syriac, much as Latin would later yield to European vernaculars. One of the monumental figures in this movement was Hunayn ibn Ishaq, whose letters, preserved in medieval manuscript collections, outline his systematic method. He traveled through Byzantine territories searching for accurate Greek copies of Galen, Hippocrates, and Aristotle, comparing variations to establish correct readings. His translations were so influential that medieval physicians in both the Islamic world and Europe referred to Galen exclusively through Hunayn's Arabic versions. His son Ishaq and his nephew Hubaysh continued this legacy, producing generations of scholars who bridged cultures through language. Beyond Greek texts, Persian works such as the medical compendia from the Sasanian Academy of Gundeshapur were translated into Arabic. Indian mathematical and astronomical treatises, including Brahmagupta's Brahmasfuta Siddhanta, arrived at the court of Al-Mansur, as documented by historians like Al-Biruni. These Indian contributions introduced concepts such as the sine function, numerical place value, and early algebraic rules, which Muslim mathematicians soon expanded far beyond their original form. As Baghdad absorbed this flood of knowledge, translation shifted naturally into commentary. Scholars like Al-Kindi, often called the philosopher of the Arabs, did not merely translate Aristotle. They wrote extensive commentaries explaining Greek logic and metaphysics to an Arabic-speaking audience. Many of these works are preserved in manuscript libraries from Istanbul's Topkapi Palace to Spain's Escorial Archive. Through such authors, Greek philosophy gained new life, filtered through a cultural lens that emphasized reason, scientific inquiry, and theological reflection. The translation movement also produced massive encyclopedic works that attempted to organize all human knowledge. The 9th century polymath Al-Jahiz, in his Kitab al-Hayawan and Book of Misers, combined zoology, anthropology, and humor with keen scientific observation. His writings, preserved in medieval manuscripts and studied by modern historians such as Charles Pellat, demonstrate how scholars integrated empirical observation with inherited knowledge. By the 10th century, Baghdad's libraries, such as the famed Khizanat al-Hikmah, were said to contain hundreds of thousands of books. The historian Ibn al-Jawzi recounts that some scholars spent their lives entirely within these institutions, copying manuscripts, debating scholars, and conducting research. Paper production, as described by al-Muqaddasi and other geographers, expanded rapidly in cities like Samarkand and Baghdad, making books affordable and fueling a publishing industry unprecedented in the ancient world. What distinguished the Islamic translation movement from earlier efforts, such as those in Alexandria or Antioch, was its universality. Every major intellectual tradition was absorbed: Greek philosophy and medicine, Indian mathematics and astronomy, Persian administrative science, Syriac theology, and logic, Egyptian alchemical techniques, pre-Islamic Arabian poetry and ethics within a single civilization. Texts from Athens, Pataliputra, Alexandria, Ctesiphon, and Antioch found common ground. As Dimitri Gutas emphasizes, the Abbasid state actively funded this process, recognizing knowledge as a tool of governance, prestige, and technological advantage. This massive ingathering of knowledge created the intellectual platform for something the ancient world had never seen, a scientific revolution grounded in synthesis. When scholars no longer viewed these works as foreign relics, but as the foundation of their own civilization, they began to expand, critique, and correct them. It was this synthesis that prepared the ground for the next generation, mathematicians, astronomers, physicians, and philosophers who would reshape the intellectual landscape of the world. Their breakthroughs did not simply continue where the translations ended. They opened entirely new fields of study, surpassing their predecessors in precision and scope. Mathematics in particular Mathematics in the Islamic Golden Age did not simply preserve earlier knowledge. It reinvented the very structure of mathematical thought. By the 9th century, the scholars of Baghdad, Basra, Samarkand, and Córdoba were no longer translators or commentators. They were innovators who reshaped mathematics into a discipline capable of describing the physical world with unprecedented clarity. Much of what modern mathematics relies on today, algebraic symbolism, trigonometric functions, algorithms, geometric proofs refined from Greek foundations, emerged from this period of concentrated genius. The turning point came with Muhammad ibn Musa al-Khwarizmi, whose books survive in Arabic manuscripts across the Islamic world and in Latin translations preserved in European monasteries. His landmark work, Kitab al-Jabr wal-Muqabala, gave algebra its name. Unlike Greek mathematicians, who expressed equations through geometry, Al-Khwarizmi presented them systematically as abstract entities, solvable through general methods. Historians such as Roshdi Rashed and Carl Boyer note that this shift, from geometric reasoning to symbolic problem-solving, is one of the most important conceptual advances in the history of mathematics. Al-Khwarizmi's work on numerals also transformed global mathematics. His treatise on Indian arithmetic, known through its Latin version Algoritmi de Numero Indorum, introduced Europe to positional numerals and the concept of zero. The word algorithm itself comes from his name. Manuscripts of his tables, preserved in libraries in Florence, Madrid, and Istanbul, show the enduring influence of his methods on later astronomers and merchants. What had been a regional Indian innovation became, through Al-Khwarizmi's clarity and authority, the universal language of calculation. Around the same period, Islamic scholars revolutionized trigonometry, a discipline only partially developed by Greek astronomers. Al-Battani, whose work was later cited by Copernicus, refined trigonometric functions by replacing Ptolemy's chord method with modern sine, cosine, and tangent. His astronomical handbook, preserved in Arabic manuscripts and translated into Latin as De Scientia Stellarum, contains tables of remarkable accuracy. Modern historians like E.S. Kennedy consider Al-Battani one of the greatest astronomers and mathematicians of antiquity, a figure whose influence quietly shaped European Renaissance science. Other mathematicians expanded this revolution. Thabit ibn Qurra, a member of Baghdad's intellectual elite and a translator of Archimedes, extended concepts of number theory, laying groundwork for integral calculus centuries later. His generalized form of the Pythagorean theorem appears in manuscripts from the 10th century and was studied by later mathematicians in both the Islamic world and Europe. In Central Asia, the celebrated scholar Abu Nasr Mansur developed formulas for spherical trigonometry essential for astronomy, geography, and navigation. These formulas appear in treatises studied by Al-Biruni, whose mathematical rigor is evident in works like the exhaustive treatise on shadows, preserved in manuscript form in Tehran, Hyderabad, and Istanbul. Al-Biruni's writings reveal a mathematical mind centuries ahead of his time. He calculated Earth's radius using trigonometric relations, determined the latitudes of cities, and introduced methods still taught in geodesy. The Islamic Golden Age also expanded applied mathematics. Omar Khayyam, famous in the West for his poetry yet celebrated in the East as a mathematician, classified cubic equations and solved them using geometric methods, a precursor to analytic geometry. His work, documented in medieval Persian manuscripts, was unknown in Europe until the 19th century, but demonstrates the depth of Islamic mathematical thought. Beyond algebra and trigonometry, scholars explored combinatorics, fractions, geometric transformations, series expansions, and mechanical calculations. Astronomical observatories, like those established under Al-Ma'mun and later under Ulugh Beg in Samarkand, required high-precision trigonometric and algebraic computations. Manuscripts from these observatories show an evolving mathematical language capable of describing planetary motion with remarkable accuracy. What unified these developments was the philosophical belief, expressed by Al-Kindi, Ibn Sina, and later by Ibn Rushd, that mathematics was not simply a technical field, but a universal language capable of revealing the structure of reality. Mathematical reasoning, they argued, led to certainty, and certainty was the foundation of all scientific inquiry. This intellectual ethos transformed mathematics from a tool of merchants and astronomers into a central pillar of civilization. The mathematical achievements of the Islamic Golden Age would become the foundation upon which Renaissance Europe rebuilt its scientific world. Fibonacci's Liber Abaci drew directly from Arabic source. Astronomy during the Islamic Golden Age grew into a discipline of extraordinary precision, driven by a unique combination of mathematics, empirical measurement, and philosophical inquiry. By the 9th and 10th centuries, Muslim astronomers were not simply copying Greek models, they were actively correcting, challenging, and surpassing them. Their observatories, treatises, and star catalogues formed the backbone of global astronomy for nearly 700 years, with manuscript evidence spread from the libraries of Samarkand and Baghdad to those of Cairo, Istanbul, and medieval Spain. The earliest major observatories were established under Al-Ma'mun, whose commitment to astronomical accuracy is recorded by historians like al-Mas'udi and Ibn al-Kifti. His researchers constructed two dedicated observatories, one in the Shamsiyya quarter of Baghdad and another on Mount Qasiyun near Damascus. There they compiled the Mamunic tables, a set of astronomical data that refined Ptolemy's Almagest. Surviving manuscripts of these tables, kept in Istanbul and Paris, reveal significantly improved values for the obliquity of the ecliptic and the length of the solar year. One of Al-Ma'mun's most extraordinary projects, described by Al-Biruni in his Chronology of Ancient Nations, was an expedition to measure the Earth's circumference. Teams of surveyors walked the plains near Sinjar and the Syrian desert, using trigonometry and stellar elevation to calculate Earth's size. Their result, within a few hundred kilometers of modern measurements, represented the most accurate Earth measurement since Eratosthenes. Astronomers of this era also developed new instruments. The astrolabe, an ancient Greek device, was refined by Muslim scientists into a precision tool used by sailors, surveyors, and scholars. Treatises like those of Al-Farghani, preserved in Arabic and later translated into Latin, describe the construction of astrolabes, quadrants, and armillary spheres. His work influenced both Islamic scholars and, centuries later, the teachings of European universities. The 10th and 11th centuries saw the rise of extraordinary figures like Al-Biruni, perhaps the most comprehensive scientific mind of the medieval world. His works, such as Al-Qanun al-Mas'udi and Tahdid Nihayat al-Amakin, survive in dozens of manuscripts across the Middle East and Central Asia. In these writings, Al-Biruni calculated Earth's radius using mountain peaks and geometric reasoning, measured longitudes and latitudes with unprecedented accuracy, discussed Earth's rotation, and suggested that the Indian subcontinent was once an ancient sea, a concept confirmed by modern geology. In Persia, the mathematician-astronomer Al-Tusi developed the celebrated Tusi couple, a geometric model that generates linear motion from two circular motions. This idea, preserved in manuscripts from Maraga and studied extensively by modern historians such as George Saliba, appears almost identically in the astronomical models of Copernicus. The Maraga Observatory, founded in the 13th century, housed hundreds of thousands of books and produced astronomical tables that later influenced Ulugh Beg's observatory in Samarkand. Speaking of Samarkand, the 15th century ruler-scholar Ulugh Beg created one of the most remarkable observatories in pre-modern history. His star catalog, compiled with a 40-meter sextant built into the observatory's structure, was more accurate than any produced since antiquity. Manuscripts of his Zg Sultani show stellar positions recorded with extraordinary precision, surpassing those of Ptolemy and remaining unmatched until Tycho Brahe. But the roots of such advancements lie earlier, in the critical corrections Muslim astronomers made to Greek astronomy. Scholars like Ibn al-Shatir, working in Damascus in the 14th century, rejected the Ptolemaic equant, a controversial device used to explain irregular planetary motion. His revised models produced results nearly identical to those later published by Copernicus. Manuscripts of Ibn al-Shatir's lunar and planetary models preserved in Damascus and Berlin show no trace of European influence, confirming that these innovations originated independently within the Islamic world. Beyond theory, astronomy served practical purposes. Accurate prayer times, Qibla determination, and lunar sighting created constant demand for astronomical knowledge. Works like Al-Khwarizmi, As Kitab Surat al-Ard, and Al-Batani, Az-Zij, were not only scientific texts, but practical manuals used by sailors, scholars, and legal institutions. Al-Batani's tables were so authoritative that medieval European astronomers referred to him as Albategnius, citing his observations throughout the Renaissance. Astronomical geography also flourished. Scholars like Al-Idrisi, working in 12th century Sicily, combined Islamic, European, and African sources to create one of the most accurate world maps of the medieval period. His Nujah, Medicine in the Islamic Golden Age, emerged as one of the most sophisticated scientific traditions in human history, blending Greek, Persian, Indian, and original innovations into a medical system so advanced that its textbooks remained standard references in Europe until the 17th century. What transformed Islamic medicine into a global phenomenon was not simply the preservation of earlier knowledge, but its systematic expansion, rigorous experimentation, and construction of institutions dedicated to public health. Much of what we know comes from medical encyclopedias, hospital records, biographical dictionaries like Ibn Abi Usaybiya's Lives of the Physicians, and surviving manuscripts copied across centuries from Cairo to Toledo. The medical revolution began in earnest with the establishment of Bimaristans, hospitals that functioned as teaching institutions, research centers, pharmacies, and public health facilities. Descriptions of these hospitals from historians like Al-Maqrizi, Ibn Jubair, and Al-Muqaddasi show institutions that dwarfed their contemporaries in Europe. The famous Al-Mansuri Hospital in Cairo, founded in the 13th century, offered separate wards for surgery, ophthalmology, fevers, and mental health, features confirmed by Waqf endowment documents preserved in Egyptian archives. Patients received free treatment regardless of religion or background, a practice noted by medieval travelers such as Ibn Battuta. This medical ecosystem reached its intellectual peak with figures like Ibn Sina, Avicenna, whose canon of medicine, Al-Qanun fil Tibb, became the most influential medical text of the medieval world. Surviving manuscripts in the Vatican Library, Escorial, and Istanbul attest to its enormous spread. Ibn Sina synthesized Galenic theory with clinical observation, pharmacology, and logic, creating a medical encyclopedia so comprehensive that European universities taught it well into the Renaissance. The canon introduced methods for diagnosing diseases by pulse and urine examination, recognized the contagiousness of tuberculosis, and advocated evidence-based treatment, a point emphasized by modern historians like John McGuinness and Len Goodman. While Ibn Sina constructed the theoretical foundation, Al-Zahrawi, Abul Qasis, revolutionized surgery. His 30-volume encyclopedia, Al-Tazrif, preserved in manuscripts from Andalusia to the Maghreb, contains detailed illustrations of more than 200 surgical instruments, many of which he invented. He pioneered procedures such as ligature of blood vessels, extraction of bladder stones, tonsillectomy, and the use of catgut for internal stitches. European surgeons like Guy de Chauliac later cited Al-Zahrawi extensively, confirming the deep influence of Islamic surgical practice on Western medicine. Innovation extended beyond surgery. The field of ophthalmology advanced dramatically under scholars like Ibn al-Haytham, whose Book of Optics not only corrected Greek visual theory but shaped medical treatments for eye disease. In Baghdad, ophthalmologists such as Ali ibn Isa, author of the Tadhkirat al-Kahalin, wrote detailed clinical manuals describing more than 100 eye conditions. Manuscripts of his work, preserved in the Suleymaniya Library, demonstrate the precision of diagnosis and treatment in medieval Islamic medicine. Pharmacology also flourished. Ibn al-Baytar, working in 13th century Spain and North Africa, compiled the Compendium of Simple Drugs and Foodstuffs, listing more than 1,400 medicinal substances and their properties. His meticulous descriptions, based on field research across North Africa, the Middle East, and Anatolia, remain among the most comprehensive botanical works of the medieval world. He built on earlier contributions from scholars such as Razis, whose Al-Zahrawi contained clinical case histories, the earliest known example of a physician systematically recording and comparing cases. Al-Razi's insistence on empirical observation, noted in medieval biographical dictionaries, set him apart from Galenic traditionalists and helped shape a more experimental approach to disease. Hospitals themselves became centers of medical education, with structured curricula and standardized examinations. The historian Al-Qadi al-Fadil, in his administrative records, describes medical licensing introduced in 10th century Baghdad during the reign of Caliph al-Muqtadir. Only physicians who passed a formal exam supervised by the court physician Sinan ibn Thabit were permitted to practice, a system unrivaled in the medieval world. Mental health care, too, received serious attention. Observers like the traveler Ibn Jubayr describe wards dedicated to the treatment of psychological conditions in hospitals in Damascus and Cairo. These facilities employed music therapy, baths, and herbal treatments, reflecting a holistic approach to medicine grounded in both empirical knowledge and spiritual understanding. The transformation of physics and optics during the Islamic Golden Age marked one of the most important turning points in the history of science, a shift from speculative philosophy to experimental methodology grounded in observation, testing, and controlled demonstration. This revolution is traceable through manuscripts, scientific treatises, and historical accounts preserved across libraries in Cairo, Istanbul, Tehran, Damascus, and European collections such as the Escorial and the Bodleian. No figure symbolizes this transformation more powerfully than Ibn al-Haytham, al-Hazan, whose writings initiated the foundations of the modern scientific method centuries before Francis Bacon or René Descartes. Ibn al-Haytham's monumental Kitab al-Manazir, Book of Optics, surviving in multiple Arabic manuscripts and medieval Latin editions, systematically dismantled ancient Greek theories of vision. Ptolemy and Euclid had argued that vision occurs because the eye emits rays toward objects, a theory widely accepted for centuries. Ibn al-Haytham rejected this explanation using experimental proofs, arguing instead that light travels in straight lines and enters the eye from the external world. His experiments involving dark chambers, apertures, and controlled light paths are described in detail across the 7-volume treatise. Modern historians such as A.I. Sabra and Roshdi Reshaped regard his methodology as the earliest clear articulation of empirical science. The Book of Optics profoundly influenced medieval Europe. Latin translations, De Aspectibus, circulated through universities from the 13th century onward and shaped the optical theories of Roger Bacon, Whitlow, and Kepler. Manuscripts in Florence, Vienna, and Paris preserve diagrams illustrating refraction, reflection, and camera obscura experiments identical to those described by Ibn al-Haytham. His insistence on hypothesis, testing, and repeatability formed the conceptual backbone of the scientific revolution. Advances in optics extended beyond Ibn al-Haytham. Scholars such as Ibn Sahl, whose works were rediscovered in modern times in a manuscript in Tehran, developed the law of refraction centuries before Snell, now known as Snell's law. His geometric proofs for bent light, especially through lenses, guided the construction of early magnifying instruments. Kamal al-Din al-Farisi expanded upon Ibn al-Haytham's optical theories in his work Tanqih al-Manazir, offering the first correct explanation of the rainbow based on double refraction inside droplets, an achievement that would not reappear in Europe until Descartes. These advancements were part of a larger shift toward experimental physics. Scholars such as Al-Biruni debated the mechanics of motion, gravitational attraction, planetary rotation, and density with striking accuracy. His works, especially Al-Qanun al-Mas'udi, preserved in Istanbul and Hyderabad, contain measurements of mineral densities that align remarkably with modern values. Al-Biruni also proposed that geological formation suggested Earth had once been covered by oceans, a hypothesis confirmed by modern paleogeology. In Baghdad, Al-Khwarizmi composed Kitab al-Jamahir, a detailed treatise on hydrostatics. Drawing on experiments with balances and water displacement, he refined Archimedean principles and proposed varying gravitational force due to altitude, a level of sophistication astonishing for the 12th century. His manuscript, preserved in multiple copies, reveals a mind attuned to precise quantification rather than philosophical speculation. Experimental chemistry, known then as alchemia, also advanced dramatically, especially through the work attributed to Jabir ibn Hayyan, Geber. Though the corpus bearing his name likely contains writings from multiple authors, the Jabirian corpus established laboratory methodology, distillation, crystallization, evaporation, filtration, and sublimation. Surviving manuscripts in Dublin, Leiden, and Cairo detail recipes for acids such as sulfuric and nitric acid, compounds unknown to earlier civilizations. These innovations eventually spread to Europe, where Latin translations of Jabir A.S. works helped form the basis of Renaissance alchemy and early modern chemistry. Meanwhile, applied physics developed through technological innovation. Scholars such as Al-Jazari, whose book of knowledge of ingenious mechanical devices survives in richly illustrated manuscripts from the 13th century, designed programmable automata, water clocks, reciprocating pumps, and mechanical devices based on precise engineering principles. His descriptions of gears, valves, levers, and rotating mechanisms foreshadowed early robotics. Modern engineers studying his manuscripts note parallels to modern automation and feedback systems. This integration of theory with experiment and engineering transformed the Islamic Golden Age into the most scientifically advanced civilization on Earth for centuries. The empirical principle, architecture and artistic expression during the Islamic Golden Age emerged from the same intellectual current that drove scientific inquiry: precise geometry, mathematical proportion, symmetry, and a worldview that saw beauty as a reflection of order in the universe. What distinguishes Islamic art and architecture from other global traditions is its fusion of mathematics, engineering, calligraphy, and spiritual imagination. This aesthetic, documented in historical works like al-Muqaddasi's Asan al-Taqasim, Ibn Khaldun's Muqaddimah, and the architectural treatises of later scholars such as Taqi al-Din, created a visual identity that stretched from Spain to Central Asia. One of the defining features of Golden Age architecture was the use of geometric design grounded in mathematical principles refined by scholars, such as Al-Khwarizmi, Thabit ibn Qurra, and later Omar Khayyam. These geometric constructions appear not only in decorative patterns but in the structural anatomy of mosques, madrasas, palaces, and caravanserais. Manuscripts from the Topkapi Palace and the Museum of Turkish and Islamic Arts preserve architectural diagrams showing how artisans used circles, polygons, and star patterns to generate infinite tessellations, an artistic language that visually expressed the concept of divine unity. Calligraphy, elevated to the highest form of art, was deeply connected to this visual mathematics. Treatises by masters such as Ibn Muqla and Ibn al-Bawab standardized proportional scripts based on geometric grids. Surviving manuscripts of Ibn Muqla's system illustrate how vertical strokes, curves, and spacing were regulated by the width of a dot, turning script into a discipline of precision. Quranic manuscripts from Baghdad, Kairouan, and Córdoba reveal calligraphers applying these rules rigorously, producing texts that were both aesthetically perfect and mathematically precise. Architecture evolved in parallel, influenced by earlier Persian, Byzantine, Roman, and Sasanian forms, but transformed through new engineering solutions. The Great Mosque of Córdoba, whose expansions are documented by the Andalusian historian Ibn Hayyan, displays a forest of double-tiered arches, horseshoe designs, and alternating red and white voussoirs derived from both Roman and Umayyad traditions. These innovations created vast prayer halls with unprecedented spatial rhythm, demonstrating a mastery of vaulting and load distribution. Further east, the Abbasid capital of Samarra showcased entirely new architectural styles influenced by Mesopotamian and Persian aesthetics. The spiral minaret of the Great Mosque of Samarra, described by medieval geographers, such as Ibn Fadlan, embodies both engineering ingenuity and symbolic meaning, its ascending helix visible from miles away. Excavations record monumental stucco carvings whose abstract vegetal and geometric motifs exemplify the flourish of non-figurative art, a signature of Islamic design. In Persia and Central Asia, architecture reached exceptional refinement. The Seljuk and Timurid eras, built upon the mathematical advances of Golden Age scholars, introduced monumental muqarnas, stalactite-like structures used in domes, vault transitions, and portals. These intricate forms, studied by modern historians like Oleg Graybar and Gulru Nekopolu, required precise geometric planning and appear in manuscripts used by architects of the era. The result was an architecture that married engineering complexity with ethereal beauty. Tilework also flourished. Cities like Nishapur, Kashan, and Samarkand developed sophisticated techniques of underglaze and overglaze ceramics. The turquoise domes that came to symbolize Persian architecture, seen in masterpieces, like the shrine of Ahmad Yasawi or the mausoleums of Merv, were possible. Due to advances in kiln technology described in treatises like the Kitab al-Dura al-Maknuna on ceramics and pigments. In Al-Andalus, architecture and science fused seamlessly. The Alhambra of Granada, though built in the later Nasrid era, reflects centuries of scientific and artistic methodology inherited from the Golden Age. Mathematical analyses by modern researchers reveal that its walls contain nearly all 17 possible wallpaper symmetry groups, an achievement unmatched by any other architectural complex in the world. Water engineering, described by historians such as Antonio Fernandez Puertas, powered reflective pools, fountains, and cooling systems that demonstrated mastery over hydraulic science. Urban planning also reached new heights. Cities like Córdoba, Baghdad, Damascus, and Cairo featured paved streets. Lighting systems, stone bridges, caravanserais, hammams, libraries, and commercial districts, forming urban networks described in detail by geographers such as Al-Baladhuri, Al-Idrisi, and Al-Yaqubi. Their manuscripts offer vivid snapshots of dense, thriving intellectual capitals where scholars, merchants, artisans, and travelers converged. Philosophy during the Islamic Golden Age became a crucible in which the intellectual inheritance of Greece, Persia, India, and the Islamic world was melted down, reforged, and transformed into a new tradition of rational inquiry. Unlike the European Middle Ages, where classical philosophy often survived only in fragments, the Islamic world embraced philosophical reasoning as a tool to understand reality, ethics, governance, and the nature of God. What emerged was a centuries-long dialogue among scholars whose manuscripts fill libraries from Fez to Samarkand. Texts that shaped not only Islamic intellectual life, but also the foundations of the European Renaissance. The earliest philosophical flowering began with Al-Kindi, often called the philosopher of the Arabs. His works, preserved in manuscript collections in Istanbul, Cairo, and Tehran, demonstrate a project of harmonizing Hellenistic thought with Islamic theology. In treatises catalogued by bibliographers like Ibn al-Nadim, Al-Kindi argued that truth is universal and must be accepted no matter its source, an idea that became a cornerstone of the intellectual culture that followed. He introduced Aristotle, Plotinus, and Proclus to Arabic-speaking audiences, and his texts on logic, metaphysics, and ethics established the philosophical vocabulary that later scholars would expand. After Al-Kindi came the great philosophical synthesis of the Islamic Golden Age, Al-Farabi, whose works are preserved in dozens of classical Arabic manuscripts. He studied logic with such precision that medieval historians like Ibn Abi Usaybi described him as a second Aristotle. His Al-Madina al-Fadila, the virtuous city, presented a political philosophy built on reason and moral excellence, while his commentaries on Aristotle clarified logic and metaphysics in ways that surpassed even the Greek commentators. Modern scholars such as Dimitri Gudas and Peter Adamson highlight that Al-Farabi A.S. work laid the intellectual groundwork for the later fusion of Islamic theology, kalam, and philosophical inquiry. Yet the Golden Age's most monumental philosophical achievement came through the writings of Ibn Sina, Avicenna, whose encyclopedic works reshaped metaphysics, logic, psychology, and medicine. His Kitab al-Shifa, the Book of Healing, and al-Najat, the Book of Deliverance, survive in vast manuscript traditions, demonstrating their immense influence across the Islamic world. Ibn Sina systematized Aristotelian philosophy into a coherent intellectual framework, introducing groundbreaking concepts such as the distinction between essence and existence, the flying man thought experiment in psychology, and new arguments for the existence of God that were studied for centuries by philosophers of all traditions. In the 12th century, Islamic Spain, Al-Andalus, became the center of philosophical brilliance, and later the platform through which Greek and Islamic philosophy entered Christian Europe. The most influential figure of this period was Ibn Rushd, Averroes, whose detailed commentaries on Aristotle became foundational texts in European universities. Manuscripts of his commentaries, preserved in both Arabic and Latin, show the depth of his engagement with Greek logic and metaphysics. He defended philosophical reasoning against critics, arguing in works like Fasl al-Maqal that rational inquiry and religious faith were not in conflict but complementary paths to truth. His ideas reached Europe through translations in Toledo and Sicily, profoundly influencing figures such as Thomas Aquinas and shaping scholasticism. Historians like Ernest Renan and Oliver Leaman note that without Ibn Rushd's commentaries, much of Aristotle's thought would have remained inaccessible in the West. But philosophy in the Islamic Golden Age was not limited to Aristotelian rationalism. Thinkers like Al-Ghazali engaged the philosophical tradition critically, refining it while opposing some of its metaphysical conclusions. His masterpiece, Tahafut al-Falasifa, The Incoherence of the Philosophers, preserved in numerous manuscripts, challenged the views of Ibn Sina on causality and cosmology. While often interpreted as an attack on philosophy, modern scholars such as Frank Griffel show that Al-Ghazali employed rigorous logical analysis and scientific reasoning, strengthening rational discourse within Islamic theology rather than eliminating it. Even in opposing camps, the debate remained fundamentally intellectual, reason confronting reason. This dialectical tradition enriched Islamic thought and inspired parallel developments in jurisprudence, theology, and ethics. The result was a culture that viewed argument, inquiry, and debate not as a threat to faith but as its natural companion. Mystical philosophy also thrived. Ibn Arabi, whose works like Futuhat al-Makkiyah survive in richly annotated manuscripts, developed a metaphysical system exploring the unity of existence, symbolic interpretation. Economics during the Islamic Golden Age formed a vast and interconnected system stretching from the Atlantic coast of Morocco to the ports of China, from the savannas of Africa to the northern reaches of Central Asia. This network, documented by geographers, travelers, and historians like Al-Idrisi, Ibn Hawqal, Al-Muqaddasi, Ibn Khaldun, and the great Moroccan traveler Ibn Battuta, created the most sophisticated global economy of the medieval world. Their surviving manuscripts, kept today in libraries in Paris, Rabat, Istanbul, Fez, Cairo, and Oxford, offer a detailed portrait of the economic engine that sustained the Golden Age. At the heart of this system lay the trade routes, overland, maritime, riverine, through which merchants, caravans, and fleets moved goods, ideas, and technologies. The Islamic world controlled strategic sections of the Silk Road, connecting Central Asia, Persia, and China with the Mediterranean and East Africa. Cities such as Nishapur, Merv, Bukhara, and Samarkand, described vividly by al-Muqaddasi and later by Yaqut al-Hamawi in his Mu'jam al-Buldan, became hubs of commercial and scientific activity. Merchants moving between these cities carried textiles, metals, medicines, spices, agricultural goods, glassware, manuscripts, and scientific instruments. The maritime network was equally expansive. Muslim sailors, using the triangular lateen sail described in treatises like those of Ibn Majid, navigated the Indian Ocean with remarkable precision. They connected Basra, Siraf, Aden, and East African ports such as Kilwa and Mogadishu with India, Sri Lanka, and Southeast Asia. Archaeological findings and historical accounts, such as those documented by historian George Harani, show Muslim merchants establishing long-term settlements in ports as far as Canton, where Chinese dynastic histories record the presence of Arab and Persian traders. These global routes required advanced financial infrastructure, and the Islamic world delivered. The development of instruments such as the sakyu check, hawala, credit transfer, standardized contracts, partnerships, merchant insurance, and letters of credit created a commercial environment that dwarfed anything in contemporary Europe. These innovations are discussed in detail in the financial chapters of Al-Qudama ibn Ja'far, is Kitab al-Kharaj, and Al-Mawardi is Al-Ahkam. Al-Sultaniyya, which remain key sources on medieval Islamic economic governance. The Islamic world's agricultural revolution, described by Andrew Watson, introduced new crops and farming techniques across the Mediterranean. Muslims brought cotton, sugarcane, citrus fruits, rice, sorghum, spinach, eggplants, and countless other crops from Persia, India, and Southeast Asia into the Middle East, North Africa, and Spain. Ibn Basal, an 11th century agronomist from Toledo, wrote detailed manuals, preserved in Arabic manuscripts, on irrigation, soil science, grafting, and crop rotation. These advances created unprecedented agricultural productivity, fueling urbanization and supporting the massive populations of cities like Baghdad and Córdoba. Urban centers became economic powerhouses. Baghdad, with its documented population approaching 1 million, maintained bustling bazaars where artisans, merchants, scholars, and travelers converged. Markets were regulated by the muhtasib, the market inspector, whose duties are laid out in administrative manuals such as those of Al-Jazari. These regulations ensured fair trade, weights and measures standardization, sanitation, fraud prevention, and consumer protection, centuries before similar institutions existed in Europe. Córdoba in Al-Andalus became a beacon of commercial and intellectual life. The geographer Al-Zahrawi wrote that its markets overflowed with goods from Africa, the Middle East, and Europe. Its libraries, public baths, textile workshops, and major industries, leather, ceramics, metalwork, made it a thriving metropolis that surpassed most European cities for centuries. Farther east, the port of Siraf in the Persian Gulf, described by travelers like Narsai and Ibn Khordadbeh, was a global maritime center through which ships carried ceramics, pearls, perfumes, glass, metal tools, and spices across the Indian Ocean. The wealth generated by this trade financed great architectural and scientific projects throughout the Abbasid realm. Economic expansion supported scientific innovation. Mathematicians developed algebra and arithmetic partly for commerce. Astronomers improved navigation for maritime trade. Geographers mapped trade routes and climate zones. Physicians studied human migration and diet through economic activity. Philosophers debated governance models that could sustain large multicultural empires. The economic stability of the Islamic Golden Age also created a wealthy scholarly class supported by waqf endowments, charitable trusts, that funded hospitals, schools, libraries, fountains, roads, and bridges. Surviving waqf documents. Al-Andalus, the Muslim-ruled territories of Iberia from the 8th to the 15th century, became one of the greatest intellectual crossroads in human history. It was here that the knowledge of the Islamic Golden Age encountered Europe directly, where Arabic, Latin, Hebrew, and Romance-speaking scholars lived side by side, translating, debating, and expanding the sciences, arts, and philosophies that had flourished from Baghdad to Bukhara. Medieval historians such as Ibn Hayyan, Al-Maqari, Al-Zuhri, and the Jewish philosopher-historian Maimonides all describe a civilization where diverse cultures intersected in ways unmatched anywhere in medieval Europe. The city of Córdoba, whose splendor is recorded in detail by geographers like Al-Idrisi and Al-Muqaddasi, became the crown jewel of Al-Andalus. At its height in the 10th century, under the Umayyad Caliph Al-Hakam II, Córdoba boasted hundreds of public baths, paved streets, advanced sewage systems, and libraries containing what medieval sources estimate to be hundreds of thousands of books. Al-Haytham II personally oversaw the acquisition of manuscripts from the East, employing agents in Baghdad, Damascus, Cairo, and Kairouan to purchase texts on philosophy, astronomy, mathematics, medicine, and poetry. Copies of his library catalog, partially reconstructed by modern historians, demonstrate a collection unparalleled in Christian Europe. It was in Córdoba that scholars such as Ibn Rushd, Averroes, and Ibn Tufayl engaged deeply with Aristotelian philosophy. Ibn Rushd's extensive commentaries on Aristotle, preserved in Arabic manuscripts, and later in Latin translations produced in Toledo, became foundational texts for European universities. His works influenced Thomas Aquinas, Siger of Brabant, and the broader scholastic movement. The historian Ernest Renan famously wrote that without Ibn Rushd, Europe might never have rediscovered Aristotle. The Jewish philosopher Maimonides, Musa ibn Maimun, born in Córdoba in 1138, absorbed Islamic Aristotelianism and later synthesized it with Jewish theology in his landmark work, Guide for the Perplexed. His writings, preserved in both Arabic and Hebrew manuscripts, further demonstrate the intercultural intellectual environment of Al-Andalus. Scientific achievements also flourished. The astronomer Al-Zahrawi, Arzakal, whose works survive in Latin translations as Arzakal's tables, invented the Sophia, a universal astrolabe capable of functioning at any latitude. His solar calculations corrected Ptolemy's estimates and influenced the Alphonsine tables used in Europe for centuries. Scholars such as Ibn al-Bana al-Marakushi and al-Petragius advanced mathematical astronomy, offering planetary models that challenged Aristotelian cosmology. While Córdoba symbolized philosophical brilliance, Granada and Seville produced extraordinary artistic and architectural achievements. The Alhambra, whose geometric patterns and Muqarna's vaulting have been studied by modern mathematicians like Marcus du Sautoy and Keith Critchlow, exhibits nearly all 17 mathematically possible wallpaper symmetry groups, a testament to the fusion of art and science in Andalusian architecture. The libraries, schools, and translation centers of Al-Andalus became the bridge through which Islamic science entered Europe. The Toledo translation movement, which began in the 12th century after the city came under Christian rule, employed Muslim, Jewish, and Christian scholars who worked collaboratively. Translators like Gerard of Cremona translated over 70 Arabic scientific works into Latin, including Ibn Sina's Canon of Medicine, Al-Khwarizmi's Algebra, Al-Battani's Astronomical Tables, and Al-Farabi's Treatises on Logic. Many of these translations are preserved today in European libraries such as the Vatican, Venice's Biblioteca Marciana, and England's Bodleian Library. Through Toledo, Palermo, and the Crusader contact zones in the Levant, Europe encountered an intellectual tradition far more advanced than its own institutions of the time. The works of Islamic philosophers, astronomers, physicians, and mathematicians entered the curricula of Paris, Bologna, Oxford, and Salamanca, catalyzing Europe's 12th century Renaissance and ultimately laying the groundwork for the later Renaissance. Even as Al-Andalus remained a beacon of scholarship, the Islamic Golden Age was beginning to experience political fragmentation in the East. Powerful dynasties rose and fell, and the unity that once sustained vast scientific institutions began to weaken. Meanwhile, new centers like Cairo, Damascus, Isfahan, and Samarkand continued producing scholars even as the Abbasid power in Baghdad waned. The next phase of this story brings us to a turning point: how political shifts, invasions, and structural transformations altered the conditions that once made the Golden Age flourish. Despite its extraordinary achievements, the Islamic Golden Age existed within a political and economic framework that was never static. Over the centuries, shifting dynasties, regional rivalries, economic disruptions, and foreign invasions gradually eroded the conditions that had supported its scientific and cultural flourishing. Yet, contrary to popular mythology, the Golden Age did not collapse overnight, nor was it extinguished by a single catastrophic event. Instead, its decline unfolded gradually, unevenly, and asymmetrically, as documented by historians such as Ibn Khaldun, Al-Maqrizi, Ibn al-Athir, and modern scholars like Marshall Hodgson and George Saliba. Several key structural changes weakened the Golden Age. One of the earliest disruptions came from within, the fragmentation of the Abbasid Empire. By the 10th century, regional dynasties such as the Fatimids in Egypt, the Buyids in Persia, and the Umayyads in Spain became semi-independent or fully autonomous. Ibn Khaldun, in his Muqaddimah, explains how political fragmentation reduces state resources and undermines the large-scale patronage systems necessary for maintaining institutions like observatories, hospitals, and libraries. The unified intellectual network centered around Baghdad began to disperse. Yet fragmentation alone did not end scientific achievement. In fact, some regions, like Fatimid Cairo, Seljuk Isfahan, and later Timurid Samarkand, continued to experience intellectual growth even as Abbasid power waned. What truly disrupted the Golden Age were the external invasions and internal economic shocks that followed. Beginning in the 11th century, the Crusades destabilized the eastern Mediterranean. While not a direct threat to Baghdad, the Crusades disrupted trade routes, drained military and financial resources, and, according to historians like Karel Hillenbrand, altered the balance of power in regions critical to scholarly exchange. Still, the scientific tradition persisted, producing major intellectual figures such as Omar Khayyam and Al-Ghazali during this period. A far greater blow came with the Mongol invasions of the 13th century. Chroniclers like Ibn al-Athir described the devastation of cities across Central Asia: Bukhara, Samarkand, Merv, once vibrant centers of mathematics, astronomy, and philosophy. Manuscript destruction during these invasions is well documented. Libraries that housed tens of thousands of scientific texts were burned, scholars were displaced or killed, and infrastructure that supported research collapsed. While modern historians like George Saliba emphasize that scientific creativity continued even after these invasions, the loss of intellectual hubs and manuscripts undeniably slowed the pace of innovation. The most symbolic rupture occurred in 1258, when the Mongol general Hulagu Khan captured Baghdad, ending the Abbasid Caliphate. Accounts from historians such as Ibn al-Fawati, who survived the sack, and later chroniclers like al-Maqrizi, recount the destruction of libraries, observatories, and institutions that had defined the Golden Age. Scholars were scattered, patrons were killed or removed from power. Baghdad's fall marked the end of the world's most important scientific center. Yet even after Baghdad, the Golden Age's intellectual momentum did not entirely vanish. Centers like Cairo, Damascus, Tabriz, Isfahan, and Samarkand continued to produce scholars for centuries. The Maraga Observatory, founded by Nasir al-Din al-Tusi after Baghdad's fall, became the greatest astronomical center of the 13th century, generating mathematical models that later influenced Copernicus. Historians like Aden Sayili and Saliba argue that this period, though weakened, still produced scientific innovation. While invasions damaged physical institutions, economic decline further weakened scholarly life. Medieval sources like Ibn Khaldun and al-Maqrizi describe increasing taxation, inflation, corruption, and the shrinking of trade routes due to geopolitical instability. The once great commercial networks connecting the Islamic world to China, Africa, and Europe began to fracture. As wealth diminished, endowments that sustained hospitals, madrasas, and libraries became less reliable. Another subtle but crucial factor was the shift in intellectual priorities. Institutions of higher education, madrasas, founded by the Seljuks and formalized in works like Al-Ghazali, Sihya, Ulum al-Din, emphasized jurisprudence and theology over philosophy and natural science. While this shift did not destroy scientific inquiry, it rebalanced intellectual energy toward disciplines better aligned with state and social needs. Over centuries, this change resulted in fewer institutional spaces dedicated to advanced scientific research. Meanwhile, Europe was undergoing its own transformation. Through translations from Arabic to Latin in centers like Toledo, Palermo, and Montpellier, Europe gained access to the works of Alki, The legacy of the Islamic Golden Age did not vanish with the decline of its political or economic institutions. Instead, it flowed outward into Europe, Asia, Africa, and eventually the entire modern world. This legacy is traceable through manuscripts, translations, scientific diagrams, nautical instruments, astronomical tables, surgical tools, architectural forms, and philosophical concepts that traveled across continents. Modern historians, including George Saliba, Dimitri Gudas, Jim Al-Khalili, and Donald Hill, as well as countless archaeological findings and manuscript studies, reveal how deeply the Golden Age shaped the foundations of modern science and civilization. One of the clearest examples is mathematics. The works of Al-Khwarizmi, whose treatises survive in both Arabic and Latin manuscripts, introduced algebra as a systematic discipline. His Kitab al-Jabr wa al-Muqabala became the core of European mathematical education after its 12th century translation by Robert of Chester. The very word algorithm derives from the Latinized form of his name. Algebraic methods developed by Al-Khwarizmi, Thabit ibn Qurra, and Omar Khayyam influenced the later work of Fibonacci, whose Liber Abaci integrated Arabic numerals and mathematical techniques into European commerce and education. Islamic astronomers transformed global scientific development through their observational precision and mathematical modeling. Ibn al-Shatir's planetary models, preserved in manuscripts housed in Damascus and Berlin, contain geometrical constructions that reappear almost identically in Copernicus' Es de Revolutionibus, a continuity documented by historians such as Willie Hartner and Noel Swerdlow. Al-Battani's trigonometric method shaped European astronomy for centuries. His values for the solar year and the motion of the apogee were more accurate than Ptolemy Elias and were used by Renaissance astronomers including Brahe, Kepler, and Regiomontanus. The influence is visible in handwritten notes found in European manuscript margins citing Alba Tegnius. In medicine, Ibn Sina's canon remained the standard medical textbook in European universities from the 13th to the 17th century. University records from Bologna, Padua, Montpellier, and Paris listed as a required text. Printed Latin editions, such as the ones from Venice in the 15th century, confirm its central role in shaping European medical education. Likewise, Al-Zahrawi's illustrated surgical encyclopedia influenced the development of European surgery. His descriptions of ligatures, cauterization, anesthesia, and lithotomy appear in later works by Guy de Chauliac and medieval surgical manuals. Optics also bears unmistakable marks of the Golden Age. Ibn al-Haytham's Book of Optics, translated into Latin as De Aspectibus, was studied by Roger Bacon, Witello, Kepler, and numerous Renaissance thinkers. Modern optical science traces its experimental roots not to the Greeks, but to Ibn al-Haytham's controlled tests, geometric proofs, and formulation of the scientific method. Manuscript diagrams from Latin Europe often replicate his experimental setups precisely. In engineering and technology, Al-Jazari's automated water clocks, mechanical devices, and gear systems constitute early blueprints for robotics and mechanical engineering. His surviving illustrated manuscripts from the 13th century were rediscovered by modern historians like Donald Hill, who demonstrated their influence on later European clockmaking and mechanical invention. Techniques for distillation, metallurgy, and chemical processes described in the works of Jabir ibn Hayyan and Al-Razi laid foundations for modern chemistry, including laboratory apparatus still recognizable today. In geography and navigation, knowledge from the Golden Age helped redraw the world. Al-Idrisi's Tabula Rogeriana, created for the Norman king Roger II of Sicily, synthesized Islamic, African, and European geographic reports into the most accurate map of the medieval world. Surviving manuscript copies reveal details about Africa, Asia, and Europe that were unknown in Christian Europe before this synthesis. Muslim navigators' knowledge of monsoon winds, ocean currents, and the astrolabe influenced Portuguese and Spanish exploration centuries later, as noted by maritime historians such as Joseph Needham and K.S. Hall. Architecture and art also left enduring marks. The pointed arch, ribbed vault, and Muqarna's inspired geometric ornament influenced Gothic architecture, as documented by architectural historians like Oleg Grabar and George Michel. European artisans studying Islamic tilework and geometric design from Granada, Seville, and Córdoba incorporated these mathematical forms into cathedrals and public buildings. Philosophically, the transmission of Islamic commentaries on Aristotle played a decisive role in shaping Western intellectual development. Ibn Rushd's writings, preserved in libraries across Europe, inspire. In the modern era, the legacy of the Islamic Golden Age has become both a subject of rediscovery and a catalyst for renewed intellectual ambition across the Muslim world and beyond. As historians, scientists, and cultural scholars examine manuscripts, archaeological findings, and cross-cultural transmission records, a clearer picture continues to emerge, one that corrects long-standing misconceptions about world history and restores the Golden Age to its rightful place as a central pillar in humanity, as scientific and cultural evolution. The 19th and 20th centuries marked a turning point in this rediscovery. European Orientalists such as E.R. Gibb, Ignaz Goldziher, and A.J. Wensink began cataloging Arabic manuscripts housed in London, Paris, Berlin, and Leiden. Meanwhile, Muslim scholars like Ahmed Zeki Validi, Shibli Nu'mani, and Muhammad Abdu worked to revive awareness of classical Islamic scholarship within their own societies. Their works demonstrated that many achievements credited to the European Renaissance had direct intellectual lineages in earlier Islamic discoveries, a fact confirmed by manuscript studies showing Arabic origins of mathematical methods, optical theories, surgical procedures, astronomical models, and philosophical frameworks. In the 20th century, as decolonization reshaped Africa, the Middle East, and South Asia, new universities and cultural institutions sought to reconnect modern scientific aspirations with classical Islamic intellectual heritage. Countries like Egypt, Turkey, Iran, Pakistan, Malaysia, and Morocco invested in manuscript preservation projects, restoring centuries-old treatises by Ibn Sina, Al-Razi, Al-Biruni, Ibn al-Haytham, and hundreds of lesser-known scholars whose works remained dormant in library vaults. UNESCO-led initiatives helped digitize manuscripts from Timbuktu, Damascus, Baghdad, and Istanbul, allowing global audiences to access these scientific treasures. The study of the Golden Age also expanded through academic disciplines, such as the history of science, championed by scholars like George Saliba, Dimitri Gutas, Roshdi Rashid, Fuat Sezgin, A.I. Sabra, and Sayed Hossein Nasr. Their research demonstrated not only the sophistication of medieval Islamic science, but also its methodological innovations. They highlighted evidence that Islamic astronomers anticipated heliocentric principles, that Ibn al-Haytham's optics introduced true experimental science, that algebra and algorithmic thinking emerged in Baghdad, and that chemistry as a laboratory-based discipline began with Muslim scientists centuries before Robert Boyle. This modern scholarship reshaped global understanding of scientific history. Universities began offering courses in Islamic philosophy, astronomy, medicine, and arts. Museums dedicated exhibitions to Islamic scientific instruments, astrolabes, surgical tools, water clocks, celestial globes, many of which function with striking precision even today. The Smithsonian Institution, the British Museum, the Louvre, and the Museum of the History of Science in Oxford all feature extensive Islamic collections that attract millions of visitors annually. Beyond academia, the Golden Age's legacy has re-entered mainstream consciousness through media, documentaries, literature, and public education. Television series, museum exhibits, and science programs showcase the contributions of scholars like Al-Khwarizmi, Ibn Sina, Ibn al-Haytham, Al-Jazari, Al-Biruni, and Fatima al-Fihri. Schools across the world, including in Europe and North America, now introduce students to the historical role of Islamic civilization in developing mathematics, astronomy, medicine, and engineering. In the Muslim world, this legacy has become a source of cultural pride and future-oriented inspiration. Initiatives in Qatar, the UAE, Malaysia, and Saudi Arabia have created science cities, research foundations, and cultural centers that explicitly connect modern technological development with classical Islamic intellectual traditions. Programs such as the King Abdulaziz Center for World Culture's Manuscript Restoration Initiative and the Sharjah Museum of Islamic Civilization highlight the continuity between past knowledge and present innovation. Just as importantly, the Golden Age has become a symbol of unity across diverse Muslim cultures: Arab, Persian, Turkic, Andalusian, African, and Central Asian, demonstrating that the civilization's greatest achievements came from collaborative networks rather than isolated geniuses. Manuscript colophons from medieval libraries reveal how scholars copied, corrected, translated, and expanded each other's works across vast distances. This intercultural intellectual ecosystem provides a powerful model for modern scientific collaboration. In modern popular discourse, however, the Golden Age is often misunderstood, romanticized as a perfect utopia or dismissed as a myth. The truth clarified by contemporary scholarship lies: the story of the Islamic Golden Age reaches its fullest meaning when viewed not as an isolated chapter of history, but as a bridge linking the ancient world to the scientific modern age, linking civilizations across continents, and linking human curiosity to human progress. As historians, scientists, and philosophers piece together manuscripts, archaeological evidence, architectural achievements, and transmission networks, a unified narrative emerges. The Golden Age was one of humanity's greatest experiments in collective knowledge. Its success was not the work of a single empire, ethnicity, or language. It was the achievement of Arabs and Persians, Turks and Berbers, Kurds and Andalusians, Africans and Central Asians, Jews and Christians, Zoroastrians and Sabians, scholars united under a civilizational culture that valued learning, inquiry, and dialogue. In the words of the great historian Ibn Khaldun, knowledge moves from nation to nation, from people to people, like the light of day traveling through the horizons. The Golden Age exemplified that movement with unmatched clarity. The foundations laid by this civilization transformed nearly every scientific discipline. Algebra, born in Baghdad, became the mathematical backbone of engineering, economics, and computer science. Optics, pioneered by Ibn al-Haytham, evolved into modern physics, photography, and quantum technologies. Astronomy, advanced by al-Battani, Ibn al-Shatir, al-Tusi, and Ulugh Beg, shaped celestial navigation, planetary science, and the Copernican revolution. Medicine, refined by Ibn Sina, Al-Zahrawi, Al-Razi, and Ibn al-Baitar, shaped global healthcare for centuries, with medical schools across Europe teaching their works until the early modern era. Even disciplines we take for granted, chemistry, pharmacology, geography, economics, sociology, architecture, psychology, contain conceptual frameworks first articulated or transformed by scholars of the Golden Age. Ibn al-Haytham's scientific method, Ibn Khaldun's social theory, Al-Biruni's geodesy, Al-Jazari's mechanical engineering, Al-Idrisi's global cartography, Maimonides' philosophical synthesis, all remain embedded in the intellectual DNA of our world. This civilization also left a cultural and ethical legacy. The translation houses of Baghdad, the observatories of Maragha and Samarkand, the hospitals of Cairo, the libraries of Córdoba and Fez, the universities of Kairouan and Baghdad, and the workshops of Damascus and Nishapur embodied an idea still vital today: that knowledge must be shared, preserved, critiqued, improved, and passed to future generations. As we examine modern manuscripts and archaeological findings, we see clear continuity between past and present. Instruments used by medieval astronomers mirror modern scientific devices. Chemical apparatus described in Arabic treatises resemble contemporary laboratory tools. Mathematical procedures appear almost unchanged in modern algebra textbooks. Even architectural techniques, pointed arches, ribbed vaults, Mokarnas, continue to influence global design. The Islamic Golden Age also reshaped the idea of what a civilization could be. It demonstrated that pluralism and tolerance, documented in the coexistence of Muslims, Jews, Christians, and others across cities like Córdoba, Cairo, Baghdad, Jerusalem, and Damascus, can fuel intellectual creativity rather than diminish it. Manuscript evidence shows collaborative authorship, mutual citations, and scholarly correspondence across religious boundaries, something rare in ancient or medieval history. Yet the Golden Age's decline carries lessons as well. Economic instability, loss of political unity, restricted intellectual freedom, and disruptions in trade and communication can erode even the greatest scientific cultures. Ibn Khaldun warned that civilizations weaken not from a lack of knowledge, but from a loss of the environment that protects and nourishes it. His analysis remains as relevant today as it was in the 14th century. As modern societies, Muslim and non-Muslim alike, seek new ways to advance science, technology, and culture, the Golden Age offers a model rooted not in nostalgia but in possibility. It shows that progress flourishes where curiosity is encouraged, where education is accessible, where creativity is rewarded, and where diverse peoples collaborate across differences. Its legacy lives on in universities, observatories, hospitals, libraries, engineering labs, and modern research institutions. It lives on in the global scientific vocabulary shaped by Arabic words like algebra, algorithm, alkali, azimuth, nadir, and alkaline. It lives on in the architectural patterns, scientific diagrams, and mathematical concepts passed down from manuscript to modern textbook. Most importantly, it lives on in the human drive to understand the universe through reason, experiment, imagination, and dialogue. The Islamic Golden Age was not merely a period of achievement. It was